Okay. Okay. Now, if I can get the marker to work, we can start. And it is not trouble. Aaron and Marissa, you can hear me, right?
Yes.
Oh, nice. I can hear you too. That's amazing. Okay. Okay. I'm having technical issues that in the 3 times I tested this never happened. So I'm mad. But if I can figure it out, I'll start. Otherwise, Marissa and Aaron will just have to like watch a video of me writing on the board, which kind of sucks.
Yeah, whatever works.
Finally. Okay. I just had to restart the program. Of course. That's always what works. Sure. Okay. Share. Okay. Now we can start. Welcome to the review. I guess let me just make a new page because the first one's bad. Hopefully I can write on this one too. Yes, good. Okay. So, who has questions? I can go through an old exam that Professor Ellis sent me. I guess, first of all, who's in Ellis's class? So we have 2 people in Erickson's class. 1 person in Erickson's class. Okay, that's fine. Ellis has an exam tomorrow, so I can just run through the review that he sent me, or you guys can ask me questions. How do you guys want to do it? Just go over the review? Okay.
If you have any questions, we'll just ask.
Well, sure. Let's start. I'm assuming he gave you guys a practice test from a previous semester already?
Yeah.
Okay. So that's the one I'm going to be going over. Same one. Seriously? No, I can't even open the test. Great. Where's the sign-in sheet? Did it make it around? Everybody signed in? Sorry, stole my pen. That's fine. It wasn't a good pen. Nope. Thanks, though. Okay, so. God, I hate everything. Sorry. God, are you kidding me? All right. Let's just. Okay. Aaron, let me know if I end up writing off of the screen for you, because I'm going to be in several tabs at once. Okay, so first question on the practice exam. Express the set of all 4-digit PIN numbers as a Cartesian product.
What year is it? What example? What example?
I'm looking at. Yes, tax day 1, 2015. So. Who knows? Without looking at the exam. This is number 1. Express the set, I guess. Do we know what a Cartesian product is?
Yes.
Okay.
Is it 2015 spring?
Tax day. Tax day is the yes, spring 2015 PDF. Oh no, wait, that's exam 1. Go back. This one. So each digit in your PIN can be 0 through 9. Your hand is up.
Yeah.
What's up? Okay. Yeah. So that's all it is. 4th power. So if I wanted to, let's say, write down all pens that can contain letters as well as numbers, and they're 6 digits long, what would I do? Anyone? Let's say they're all lowercase letters. Add A through Z. So this is the set of all digits and all lowercase letters, and it's a 6-digit password. And again, if I have like a 2-character password, one with a letter, or the first character has to be a letter, the second letter has to be a number, right? There you go. I hope this was too easy. That's why everybody looks confused. Okay. What? Oh my God. Okay. Okay. Describe how a partition of the set of integers. Describe a partition of the set of integers into 2 infinite sets. Okay. What's the most obvious choice if you're going to separate them into? Not you. You clearly know the answer. Somebody who isn't paying attention. Do you guys have particular questions? Because the first few questions on this thing are super easy. I would prefer to answer questions than to just go over the exam. How about this? I'm going to skip to induction. Huh?
Can you do number 5?
Number 5. Sure, I'll do number 5. What does this algorithm do? Compute x, y, and input x is real. X and y are both real. And n is non-negative. N is non-negative, whatever. Hi. Here's the assignment sheet. Just write down your name and number. And then what's it do? It outputs z. Okay. Outputs z. If n equals 0.
Which one are you doing?
Number 5.
Okay.
Compute x, y, and compute c, y, return c. Okay, so the question is, what does this algorithm do? Well, all right, so we're looking at exam 2 from 2015. It says tax day at the top. That's all I know. So we want to know.
You have a version of the exam than you have a different
Seriously?
version of the exam than some people.
Than some people?
Well, I mean, the one that I printed out from Alice's website is just has the questions in a different order, which is where I think the confusion is coming from.
Do you know what question this is?
On my exam, it's question 10.
Okay. Is this question 5 on your exam? Okay. So at least it's correct on yours. Okay, this is either question 5 or 10, depending on what version of the exam you're looking at. Wonderful. That's awful. Okay. But I've written it on the board, so you shouldn't have to find it in your PDF. So we put in 2 real numbers and some integer that's non-negative. If the integer is 0, we return x. Okay. If otherwise, we do it again with x, y, and n minus 1. And then z is x plus y, and we return z. But if n is not 0, well then, return me. Whatever. Sure, here's that. If n is not 0, we reduce it by 1 here, and then we add x plus y. So if n is 5, what we're going to do is we're going to add x plus y, and then we're going to go down to n equals 4. And we're going to add the yes. We're going to where's the sign-up sheet? Make sure it gets to the back, please. Okay, well let's think if n equals 1. If n equals 1, we skip the first line, and we go to the second line where we compute x, y, 0. And that's going to give us x. This equals x here. So then, for n equals 1, z equals x, and then z equals x plus y. I don't like this. Okay.
What is the interesting? What is the interesting?
Z equals z plus y. Okay. God, no wonder I'm so confused. Z equals z plus y. So z equals x, and then z equals z plus y, so z equals x plus y. So then if we plug in n equals 2, we're going to skip the if line, and we're going to go here, and we're going to get x plus y for z. Then we're going to z plus y. So for n equals 2, we're going to have x plus y from here plus y. Yes? It's an input. And I'm adding it every time because that's what this line says. This line here. And x and y can be any two real numbers. So I think, and then if n equals 0, we get x. If n equals 1, we get x plus y. If n equals 2, we get x plus y plus y. So what does this algorithm do? Can anyone tell me? Except for you. Stop it. So it looks kind of like we're always going to get x, right? X plus something. What is that something? Not quite. N times y. That's what this algorithm does. It computes this number. Yes. Which Professor Ellis, in the key to his practice exam, and writing it this way, he says, it produces the nth term in the sequence x plus y, x plus y plus 2y, which is an arithmetic sequence. Do you guys need to know sequences for the exam? Yes, okay. So then it's good to know that this is producing the nth term of this arithmetic sequence. Does it make sense? Since you're the one who picked up this question. Which part don't you understand?
The x plus y when you watch.
Here? So what happens is if n is positive, we go down to the next one. And then we keep doing that. And then after that, after we've gone down, so if n is 5, we're going to hit this line, and we're going to compute all the way down to 0 until we get x. Nothing is really happening because we're just running the algorithm over and over again until we get n equals 0. So we're going to run it for 5, 4, 3, 2, 1. And then when we run it for 0, it'll return x. Then on this run, z equals x, and then z equals z plus y. So that, since we get x here, then in this step, z adds y to itself, so we get x plus y. Now in the next step, 2, z is x plus y, and it adds y to itself, z plus 2y. And then that goes on for whatever n is. And that's how you get this x plus n times y.
Can you bring that line, the first C line? Yeah, that one.
This one?
Yeah. What's the job of that line?
This line, let me rewrite it. I wrote it poorly. It is setting z equal to whatever this algorithm returns if you decrease n by 1. So that's why I say if n is 5 at first, you don't actually get any answers until you go all the way down. Because at each step it says, well, z is, all right, do it again. Until you get down to 0. Then z becomes x. And then the next line, it becomes x plus y. In this one, it becomes x plus y. So it's a recursive algorithm. Anyone else have questions? Okay.
So, can you do number 6?
Number 6? Sure. Give me a moment. Oh, what? You're not kidding me. Please. Okay. Fine. I don't know how to use this program. Okay. 6. A geometric sequence. How does a geometric sequence work? Anyone? Just shout it out. How does a geometric sequence work? In one word. Yeah, there you go. Multiply. All right, so you start with a number. Let's call it A. Why not? And then, so we'll call this the 0th term of our sequence. So then what's the first term? Ka, I guess. And then what's the second term? Yes. Just because I'm making stuff up. Okay, so we know that the geometric sequence has first term 5 and has fifth term. So this is the 0th term, and the 5th term is 12. So what's the 5th term? Using this k to some power a thing, what is this? Yes. K to the 5th times 5. And the question says solve for k. Right, so I guess let's...
So the first term is A, not the 0th term.
You're right.
Yeah.
Okay, so that's k to the 4th. It seems odd. He used 0 in the last one. K to the 4th. That probably makes it better, though. So we divide both sides by 5. And someone should definitely be able to do this. I know that this is 16 squared, so k squared equals 16. I just know that. So now what's k? Plus or minus 4. Be careful. Probably plus or minus is going to be important. But, yep, k equals 4. Ta-da, that was what the question was asking.
Yeah, here is 4.
4, sure. That's how we do it. Four. Define f of n to be 5n cubed plus 2n plus 1. 2n plus 1. And g of n is n squared plus 3n. All right, simplify the asymptotic complexity. Wait, no, sorry. What? Oh, yeah, okay. Simplify the asymptotic complexity of each. So find big theta of f of n. Sure. Yeah, pretty much, yes. So big theta of f is just going to be in we write it as theta of n cubed.
So is there like any steps to it, or do we just write it?
No steps. I don't know what steps you would write unless
Finding
Did-
K.
unless he asks to find C and K is the constant.
Yeah.
The smaller things are K. If he asks you to do that, then yes, but
He doesn't.
he doesn't. He just says find the asymptotic complexity. So he saves you lots of time. So then what's theta of G? Somebody who hasn't spoken yet. Ha! Or just shout it out. N squared. Let's do something slightly more difficult. All right, what's theta of F plus G? N cubed, because G just adds an N squared term, and we still only care about the biggest one. And last one is F times G. Theta of F times G. Did I hear an answer? No? Anyone? So since we still only care about the biggest power of n, we could multiply everything together, or we could just multiply the two biggest ones together. So we have n cubed times n squared. So what is that? N to the fifth. Make sure you don't write n to the sixth. Just saying. Easy thing that people like me still screw up. How's that for time complexity? Cool?
Yeah.
Better? Okay. Just the biggest guy.
Should we do 7?
7? Sure. Seven. You have a relation R on the set 1 through 7? 1 through 8. 1 through 8. I refuse to write them all down. A is related to B, provided there exists a prime factor that divides both A and B. Can I just say that? A is related to B if there's a prime factor that divides both of them. K divides A and K divides B. I don't know if you've used this notation, but I don't write out all the English. So like, are 4 and 8 related? Yes. They're related because they're both divisible by 4, or no, 2, because we have to be prime. Okay. Draw the arrows to complete the dots and arrows diagram. Oh, I should have written out all the numbers. Okay. Sure. So we're going to write the dots and arrows diagram. And this is going to be kind of a disaster because I just wrote them in a cycle instead of thinking about it. So, who's 1 related to? Close. Nothing. 1 is related to nobody because 1 is not prime. There's no prime number that divides 1, so there can't be a prime number that divides 1 and somebody else. So 1 is related to nobody, not even itself. Okay, who's 2 related to? It is related to itself. I don't want to draw circles around everyone. So it's related to itself. I'm going to go ahead and claim that these are all obvious, right? And I guess these arrows go both directions, but that's fine. Well, is this relation symmetric? I guess before I double the arrows, is this relation symmetric? If I have ARB, do I also have BRA? It's just like asking, can I rearrange this thing? Yes, I can rearrange these things. So it is symmetric, which is the what? Second question? Yeah. So then we get double arrows on everything. Then 3 is related to 6, and only 6, right? Yeah. And itself, of course. Everybody's related to itself except for 1. 3 is related to 6. 4 is related to 6 and 8. 5 is related to just itself. Yep. Cool. And at that point, because all the arrows are doubled, we'll be done. Because we've already covered everything. Except for 7. Sorry, I lied. 7 is related to itself. Okay, so is it transitive, I guess? So I'll draw some more arrows. You might get.
5 divisible by 2.
I mean, everybody is. So. Sure, okay. His drawing's much more complicated because instead of just putting double arrows, he has 2 one-direction arrows. So is it transitive? I guess, is it reflexive? Let's go in order. Is it reflexive? What does reflexive mean? Louder. Yes. A is related to A. Okay, so is this relation reflexive? No. This guy's a problem. If the set were defined differently, just 2 through 8, then we'd be good. It would be reflexive, but it's not. Symmetric, we just talked about, because there's no implication here. There's no ordering that matters with A and B. If they're both divisible by a prime, like, it doesn't matter what order you consider them. If you drew out the whole picture with single direction arrows, you'd notice that all of them were going both directions.
So if we have, let's say that the question was 2 different sets. I mean, yeah, like 2 different identical partitions, so another partition.
Sure.
Okay. Yeah. And the other partition looks just exactly like that, but they're not related to each other. Can I still say that they're reflexive? It will be without the 1.
A relation is defined on a set.
Yeah.
So if your relation only had arrows across 2 sets, then, I mean, it could not be reflexive, for example, because the relation puts arrows on the relationship.
Yeah.
And if you have to go across between the 2 sets, it means you can't be reflexive because you can't have a loop.
Okay.
So usually this picture is usually of a function. Functions go from one set to another set or from one set to something. It might be the same set, it might be a completely different set. Relations always come back to the same set. Oh, is it transitive? I guess is the last question here. If I have A is related to B, and B is related to C, is A related to C? This is beeping at me because I'm outside the lines or something. So the guys online can't see all that.
Is 3 related to 6, 6 related to 4, and 3 is not related to 4.
Right. 3 is not related to 4.
Which is not transitive.
Right. So it's not transitive. Correct. There you go. Find an example. Show it's not transitive. For anybody who didn't hear, he said 3 is related to 6, 6 is related to 4. 3 and 4 are not related though. So there you go. So, here's another one about what does the following algorithm do? Do we want to do another one of those? Is that a yes? Input. A list of numbers. I guess they're ordered. A1 to AN. Put X. X equals 0. A1 is greater than AI. Increment X. And for return, just return, right? Return X. Okay, so we have a list of numbers. And from 2 to n, we say this guy's the most important, kind of, right? Because we're at every step we're checking whether he's bigger than somebody. So what we're doing is if A1 is bigger than A2, increment X, then do the same thing for every other thing in the list. So if A1 is bigger than A2 and bigger than A3, but smaller than the rest of them, what do we get? So in this loop, we say a1 bigger than a2? Yes. X becomes 1. All right? I equals 3. a1 bigger than a3? Yes. X equals 2. All right, 4. a1 bigger than a4? No. Because I have decided. So then this will loop through the rest of the entries in the list, and X will never change. Because X only changes when A1 is bigger than something else. So describe what this algorithm is doing. Someone. Or I could just say it. Or you could say it. Sure. That's not how I would say it. I wouldn't say count the number of times that this guy is biggest or bigger between two things. I'd say count how many of these guys are smaller than A1. And I believe that's exactly what he says. Yes. It's just a cleaner way to phrase the same thing. Okay, let's talk about a function. We did a relation, now let's talk about a function because a question. Everybody's good on this, right?
F goes from 1 to 4, A, B, C.
F of 1.
C, F of
2.
B, F of 3,
C again, and 4. Okay, so write down the set description of F. What does the set description of a function look like? It looks like a list of ordered pairs, right? So what does the set version of this function look like? Yep. It'll be 1C, 2B, 3C, 4A. Okay, what does the for F inverse look like? Yeah, flip them. I don't want to write it. Okay, is it invertible?
No.
Why not? You say no. Why is it not invertible?
Is you have two domain and match with one time.
Right. Yes. When you take the inverse, you get C1 and also C3. So the inverse is not a function. So it is not invertible. Well, at this point, I don't expect anyone else to show up. So I'll just take that. Questions on functions at all? Is this function one-to-one? Nope. No. Is it on to? Yes. So, yeah, it's half good. Okay.
Let's skip 10 and go to 11.
Sure, let's go to 11. Oh, man. Okay, binary string of length n. That's n zeros and ones. Cool. The unique binary strength of length 0 is the empty string denoted by lambda. This question develops a recurrence for the number of binary strings length n that do not have two consecutive ones. Okay. Make a new page here. Okay. So write down all the binary strings of length 0, 1, 2, and 4 that do not have two consecutive ones. Length 0. There's 1. We call it lambda. It's the empty string. All right. How many binary strings of length 1 are there? 2. 0 and 1. How many binary strings of length 2 are there? Okay, yeah. There's 4 of them, but one of them has a repeated 1. So we only care about 0, 0, 0, 1, and 1, 0. 3. I guess we just write them all down. So 0, 0, 0, and then 0, 0, 1, 0, 1, 0, 1, 0, 0, and 1, 0, 1. That's probably all of them, right? Am I missing one? No, that's all. And I guess the idea is you'll write down all binaries and figure out that only 5 of them work. And then length 4, that's exactly what he did. He wrote down all binary strings of length 4 and then crossed out all the ones that had repeating ones. I don't feel like writing them all. So we won't, just because I'll just tell you there are 1, 2, 3, 4, 5, 6, 7, 8. There are 8 of them. B. Consider all the strings of length 3. For those beginning with 0, chop off the first digit. For those beginning with 1, chop off the first 2 digits. So this was A. B. For anything starting with a 0, chop off the first digit. We get 0, 0, 0, 1. This is 1, 0. And then chop the first 2 digits of these guys. We get 0 and 1. That's funny. This is all the binary strings of length 2 that don't have a repeated 1. This is all the binary strings of length 1 that don't have a repeated 1. Define a recursive formula to count them. So okay, I'm going to write down the strings of length 4 that don't have repeated ones. Just so we have them all written down. Of course. Two, three, 4, 5, 6, 7, 8. Cool. Let's do the same thing here. Let's chop off the first 1 if it starts with a 0, and the first 2 if it starts with a 1. So we end up with 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0. Jump over here. 1, 0, 1, 0, 1, 0. No, sorry, that's fine. Okay, so yeah, and then chop off the first 2 for everything that starts with a 1. We get 0, 0, 1, 0, and 0, 1. So we see it again. This is all the binary strings of length 3 that fit the correct description. This is all the binary strings of length 2 that fit the description. So I think at this point it is reasonable to conclude f of n equals f of n minus 1 plus f of n minus 2. Right? Everyone else think that's reasonable? It might not be correct. It seems reasonable. We found already 2 examples that fit, and it seems weird that that would happen. Okay, and now we want base cases for this guy.
Third question. 0, 1, 0, 1 is the third one.
Hmm?
The third one is next one. Should be 1, 0, 1 because you start from 0, so you jump on 1 digit.
This one, 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 this one. Because I wanted to stick all my 3s together and then have my 2s later. I wasn't thinking about that when I wrote down these ones. So base case, what, f of 0. What is f of 0? 1. Yeah. What is f of 1? 2. And now you know f for all values of n, as long as you have a fast enough computer. Use the recurrence to compute f of 8. How do we do that? So that would be f of 7 plus f of 6.
Question. Is it have 0 equal 1, which is still
Yes. This counts as a string. It is the empty string. It looks like this.
Count 1.
Hmm?
Count like number 1.
Yes, it counts as one string. Is that your question? Yeah.
And do we so to have two starting points, we base ourselves on the formula, saying that n minus 1 is n that we need to make the recursive relation.
Right. Yeah. We find a recursive formula that depends on the guy before me and the guy before him. So
We only need 2 cases.
yeah, we need 0 and 1. Or I guess if 0 is too hard, we can do 1 and 2. But 0 and 1 is best. F of 7, we want f of 6 plus f of 4. And then we have another f of 6 here. Oh, sorry, that was dumb. f of 6 plus f of 5 plus f of 5 plus f of 4. We know this one. We know this guy's 8. So this guy is going to be f of 5 plus 8, which is f of 4. And then this one's going to be f of 4 plus f of 3, which is 5. Same with this guy. It's going to be 8 plus 5. And the last one's going to be 8. And f of 5, I just computed, is this guy. So that's going to be 13 plus 13, 13. 3 times 13 plus 8 plus 8 equals 55. 39 plus 16. Yeah. Yep.
What's the number? So here we're doing all of them. We're going back to 1. But what's the general rule for if we were to have all the strings of length 4? What is it, like 2 to the something or
2 to the 4.
it would be 2 to the
Yeah.
length? Okay.
Right. If you have all binary strings of length n, then you have 2 to the n of them, because it's a product of this guy. And when you have a Cartesian product, you just multiply the number of elements. So
What is the ideal? What's the ideal? The result you get there is a party.
yes, for part D. Yeah.
Is that the 8 plus 5? The one that is in the square?
This 8 plus 5 came from finding f of 5.
Okay.
So I just skipped from, I didn't want to write down f of 4 plus f of 3. I just wanted to write down 13, 13, 13, and 16.
What's a good way to come out with a relation? To come out with a recursive relation? Is there any procedure, I guess?
To come up with a recursive relation.
Is it a recursive relation, right? Or not?
Recursive function.
Recursive function.
Relations and functions are different. The easiest way to come up with a recursive function, it doesn't need to have some actual meaning. Like here, the meaning is binary strings without adjacent ones. But you could just define a function that says, well, each number is the sum of the previous 2 numbers. And then you get something like the Fibonacci sequence if you have, well, actually, this will generate the Fibonacci sequence.
Yeah.
Usually your base cases are 0 and 1. But it doesn't matter. So it's easy to construct a recursive function that just produces numbers, because you can make whatever number you want just by adding things together.
Did you do this one?
12? Yeah, let's do 12. Everybody's good on this, right? I'm not going to write down the name. Does everybody have a copy of this exam? Does everybody have a copy of this exam?
Yeah. Do you remember what you're doing?
Huh?
Are you sure?
I'm I'm still looking at the same exam. Does everybody have a copy of it?
Yeah.
Because I don't want to write out the algorithm.
Oh, okay.
I think everybody watching online left.
I'm still here.
Oh, no. Aaron's still here. Aaron, you have a copy of the exam though. So
I do. That's
okay.
not the version that you have, but it's similar.
Okay. Hmm.
It's fine.
I'm already started. I'll sketch. Output. What? Output. A1 through AN with AI equals average of x1, xi. So each A is going to be the average of the first I numbers in this list. Okay. But we just want to talk about time complexity. So for I equals 1 to n, I equals 1 to n. AI equals 0. Or j equals 1 to I. AI equals AI equals xj. And for AI equals AI prime. AI equals AI, so I. And then N4 and turn. Okay. Let's start from the inside and work out. How many operations are being done in this line? Two. Yeah. We're setting something equal and we're adding some things together. So this is 2. But how many times does this box? This box is so 4s have a hidden 2 inside because they set something equal at the beginning and they increment at the end, kind of, or they check something. So there's always going to be a 2 in here. This box will execute 2 times, if we're going from 1 to I, we're going to have 2I times number of operations inside.
What was the 2 again?
We're going from 1 to I, but the way that for loops work is that hidden inside the for loop is a 2. Because kind of at the beginning you set it equal to 1, and at the end you set it equal to 1 plus 1 or something. So you're always going to have 2 times the number of iterations times the number of operations inside.
So it's because it's going from here to here, so it's doing, I guess, well, the 1 is because you're doing like,
Does he have another explanation?
She wrote the answer in the back.
So for j equals 1, that's one operation. And then it's going to j. So it's going to be 1 times every single one of those things, right? Because it's equal to every single one of those i's.
Kind of.
So that's still 1.
He writes down loop bookkeeping.
Yeah.
Which,
So like updating those?
and keeping track of where I was last time, kind of. So at the beginning, we say it kind of starts as j equals 0, then increment j equals j plus 1. Do this. Go back. Now j equals 1. J equals j plus 1. Now do this. So I guess each step is j equals j plus 1, which is 2 operations. Okay. And I forgot to do this. Okay. So I approach this differently than he does. So this is 2 operations, right? But how many times does this thing execute in this loop? Yes. It loops I times, yes. Then this outside loop also is 2i operations, right? Because of the bookkeeping. J equals j plus 1 each time. So this one gives you 2i as well. But they're also hidden inside this for loop. So really, each one of these guys is going to be I starts at 1 and goes to n, and then so this is going to do 2 operations, and then I goes up, and then we get 2 times 2 operations, and then I goes up, and we get 2 times 3 operations, right?
What is it? 4 times operation. You're getting 2 and 2.
Plus, oh, because I'm saying both of them look like this. So if we want to do them together, then let's do 4. That's fine too. So this whole box is going to do this many operations. Yes. Then this guy is going to do how many operations? In a single iteration, it sets equal. It does 1 operation, but it's inside a loop that goes from 1 to n. So this thing does 1 operation n times. And this thing does 2 operations n times. Then this guy also does 2 operations n times. Because this is where the bookkeeping happens. Yep.
The last one, AI equal AI divided by I.
Mm-hmm.
So the first operation is divide.
Yes.
And then the second operation is assign.
Yes. The same way this is 2 operations. Plus and divide are the same. They're both 1 operation. And then setting equal is also 1.
Where the 2 operation comes from? Can you say that again? So if you divide is 1, right?
And assign.
Oh, and the assign is 1.
Yeah. Equals is an operation because I'm
I'm
setting AI equal to something that I have to do 1 more operation to find. Then the big loop also does 2n things because bookkeeping. So we have 5n plus 4 times the sum from I equals 1 to n of I plus 1. Where does 1 come from? I think we have 1, don't we? Oh, you gotta be kidding me! I have to restart something. Yeah, what? Somebody tell me where this 1 comes from.
Return.
Yep, the return, exactly.
Why is there no sum for the outer 4?
The inner for loop, so the inner for loop loops from 1 to I, right? But it does it for changing values of I. This sum comes from a double for loop. This one's just a single for loop, so you just multiply by how long the for loop is. But since this one is a for loop inside of a for loop, you multiply by how long the for loop is, but then you also have to make sure you do it at every step of the big for loop. So for every value of I, you're going to do 4 I operations. And the values of I range from 1 to n. So then you add them all together, and that's how I get the sum. Yes, and then come back here and share. Okay. Sorry if you got lost for a minute there. Okay, yep, so this comes from the thing. Somebody tell me what this is. You guys should. N times n plus 1. Yeah, right. So this thing. Sorry. Yeah.
Just based on faith.
So then this thing is 2. This guy is n squared plus n over 2. We multiply by 4, we get 2n squared plus 2n from here plus 5n plus 1.
Why you get 2n squared? Oh,
There is, yeah, okay. So this is what you get. I believe there's an error in the answer key. He says he says 4 times this, and he loses the 2. You've got 4 divided by 2, but he loses that 2. So he's got n squared plus 6n. But right, I think he just missed that.
The theta is the same, right?
Theta is the same. Yep. What is theta? Yep.
We always say there's time complexity in terms of beta, right? We don't use the omega, the big omega, or the big O.
Correct. If you want to talk about how long it takes an algorithm to run, you almost always want to use theta.
Which is the time complexity. That's
Right, that's this one. So there were no conditionals. There were no ifs here. So if we had an if statement inside somewhere, then we'd say, well, it's big omega of the number of times we had to do something when if was true, or I guess the upper limit of the number of things we have to do, and then omega is the lower limit. Omega is the lower limit of how many things we have to do, and O is the upper limit of how many things we need to do. So if this thing were 4, whatever, and I equals 0, if I is even, I guess, I don't know. It takes some number of operations to check that, but let's just assume that we can check this in 0 operations. If we had this if statement here, then this loop would only happen half the time.
Yeah, so you have
So-
upper bound and lower bound.
Yeah, so this would be much smaller. This would be the same, because all I did was make the algorithm shorter.
Okay.
But
and you analyze
this thing would
both
be
cases,
small.
and that's why you're
Right.
No, so like say like the initial for loop 40 from one side, but from like I equals 2 to n.
Yeah.
Would it be 2 times n minus 1 operation instead of 2 times n operation?
Yeah, it's 2 times the number of things in here. So if you go from 2 to n, that's n minus 1.
Oh, okay.
And that's why this thing is 1 to I.
So for all like this, the loops, it's always going to have that two bookkeeping, so you always just account
Yeah.
So the bookkeeping will be just basically saving the value into the variable, right? And
The bookkeeping is j equals j plus 1.
yeah.
It's addition and set equal. So at the beginning, you know what j is. For j equals 1 to I, you know what j is the first time. But then the second, then here, kind of, somewhere inside the loop, you have to make j bigger. So you have to run this code somewhere. So we just say that bookkeeping is 2 operations per step because you have to keep track this way. $13. Oh yeah, here we go. Here we go. New page. F goes from A to B. G goes from B to C. Both are on 2. Prove G composed with F is on 2. I heard the word picture. I don't think that was related, but I'm going to draw a picture. Okay, good. I'm glad it was
I was saying that I was trying to use that as my proof, and he didn't have it.
You need to do more than just draw the picture. Okay. So, what does onto mean?
So they
All the things in the target have something pointing to them. Yeah. So there's some subset of A that points to everything in B. And because G is also F, and G is also on 2. So what you want to say is, what you want to prove is for all C, there exists an A such that G composed with F of A equals C. That's what we really want to prove. Did everybody know before I wrote that down that that's what we want to prove? No. Okay. Onto means, so what did we say onto meant? Onto meant everybody in the target has someone pointing to them. Was it everybody in the target, sorry, has someone pointing to them. Well, this means has somebody. So now I just rewrote it, but with this function instead. This function is called G composed with F, and it goes from A to C. A to C. So if this one makes sense, this one is only slightly more complicated. No, that's easy. It might take a while, but it's not hard. We say, all right, well, pick a C. Let's see. This is bad form. What is he? He says, let Z in C. Good for him. He's more careful than I am. Okay. Well, we know that G is onto. So there exists B such that G of B equals C. Since G is onto. Okay, but for every B, there exists A such that F, I have to use this one, magic erase. F of A equals B, since F is onto. This is obvious now, right? For any Z, I like little c. I like naming them as the little version of the set. That's just how I am. For any C in here, I can find a B that points to it. And I can find an A to that. I don't know how you write QED. That's how I... Ta-da!
That's better.
Since G is onto, there exists... he wrote English. This is the only English word in my proof. What he wrote was, since G is onto, there exists a B, he says Y.
He's like saying to observe this, like, do we need to put that to be the proof, or is it just not okay?
Observe is what I just finished saying but not writing down. Observe, I mean, that's fine. When he says observe, he's saying, observe that, oh no, well, he's saying, okay, after we go through this proof, now we have some A, right? When we went through the proof was, well, we found an A here, such that f of A equals B, and G, okay, sorry, let me rewrite it somewhere that's not making the machine angry. we found an A such that f of A equals B, such that G of B equals C. And this is another way of writing G composed with f of A equals C. And this is what observe says. So yeah, maybe write that down. Instead, don't point to your exam during the test and say it like I did.
This exam so well.
Last one? Uh-oh.
We're gonna have a hard time doing it. Did you study?
Does everybody know induction?
No. Can you go over that?
Okay, so induction is not on... Oh, wait. No. What? Oh, I found the other versions of the exam.
You don't go in the bottom?
It's W.
Now I feel dumb. Okay. So, induction will probably be on your exam. I wasn't expecting it not to be on the practice.
Maybe in the...
It doesn't matter. Okay, thank you for realizing that it doesn't matter. I'm going to open up a new page and rant about how strong induction and normal induction are the same. Because I feel like this is useful to people to understand. Induction is like saying, all right, I'm going to set up a bunch of dominoes. That is your recursive formula or whatever. Then you prove your base case, and that's knocking over the first domino. So I think that induction is always done in the wrong order. I think that you're always taught, all right, find your base case first, and then do your inductive hypothesis, whatever. But the inductive hypothesis is the intuitive part. Like, if something's true for n, I'm not going to write it down. If something's true for n, and you can show it's true for the next thing, whatever that is, you just knock down your dominoes. Or I guess that's, if you can show that you assume that it's true for n, then you can show that, well, if that were true, then it would be true for n plus 1. That's setting up your dominoes. Then you prove it for 1, and you knock down all the dominoes. Strong induction is just, well, I need the 2 dominoes behind me to both be true. It's all the same. The proof works exactly the same way. You can do any proof by induction. Any proof by induction says assume f of n is true. Show f of n plus 1. F is probably a bad letter to use, but fine. Okay, what does strong induction look like? Assume f of k such that k is less than n. How is that different? Here, it's just a special case. It's just like, well, here, if you're asked to use weak induction, it means, well, I only need n. I don't need anything earlier than that. But strong induction. So if you want to prove something about the Fibonacci sequence, we call it strong induction because you need 2 things instead of just 1. But really, you just assume, well, everything before me is true, and you just do it that way. So I'm glad that at least some of you understand that they're really the same. The thing that drove me crazy when I was taking this class is that no, I'm a math major. I loved this class, but the thing that really bugged me about the class was strong induction is treated as if it's different. And it's like, use strong induction for this, use weak induction for this, but it's all the same. And if you understand strong induction, normal induction is just the same thing, except
Can you
easier.
do an example for induction?
I might just have an example for induction. Okay. I have your activity from class for strong induction. So do we want to do induction or number 14? Okay. Well, I don't know if I can finish both in 20 minutes.
Induction.
Induction? Okay.
Can you not do the activity though? Like, if that in class?
Yeah, the activity's not really.
There's a 21 on an exam. Is it final exam?
You're holding it.
I am.
Every time I try to do something new, the machines hate me. So I'd rather just use the paper. Already erased the board. Okay. This one? Number 21? Prove that AN is odd. Yeah, that's not like induction. A3 is 1. AN equals AN minus 1 plus A minus 2 plus AN minus 2. For all N, at least 1. AN is 33.
Right.
2 hours, man.
He timed it spend like 40 minutes on true or false, 30 minutes on the
I had 17 questions.
So, okay.
40?
So,
What do you think?
if you have to explain the difference between strong and, does he call it just induction or does he call it weak?
Just induction.
Good. That's better than weak induction. The difference is that in normal induction, you only assume. Not quite correct. You only assume n. Let's say we want to prove n. Then you only assume n minus 1. And you don't care whether n minus 2 is true. Strong induction is, well, assume for k less than n. So that includes this, but also everything before. Strong induction, it's not just you only have one base case, because you might still only have one base case if you have some weird function that, like, I don't know. The important thing is that the thing that makes it strong is that it's already true for almost everything. So you can use anything less than n. Like if I had an equals an over 2 plus e to the negative n, I don't know, make it an integer or something. I'm probably going to need lots of things earlier than n to be true. Much more than n minus 1, n minus 2. But strong induction can still handle something like this because I already proved that it's true for everything. E to the minus n makes no sense. I'm sorry, but that's fine. Cool. That should be everything you need to know about the difference between strong and weak induction. It's all strong. Weak induction is really just like strong induction when he's not trying very hard. Okay, prove that AN is odd. Well, assume. I'm going to do it my way instead of Professor Ellis's way. Assume AK is odd for K less than N. Sure. All right, now an equals an minus 1 plus an minus 2 plus an minus 3 equals what? Okay. Now the important thing about a proof is applying this guy. Mostly this guy. Because this guy is just true for everything smaller. AK is odd. All right, so what does that mean I can do about this? It means that each one of these, I can write AK as 2. I'm going to put a subscript on K because I'm going to have a lot of them. 2K1 minus 1 or plus 1. Your choice. It doesn't matter. Let's use plus. So maybe I should use H. H. Is that okay? Do my H's suck? So an minus 1, I'm going to write it as 2 times hn minus 1 plus 1 plus 2hn minus 2 plus 1. Right? This is an minus 1. This is an minus 2. Plus 2hn minus 3 plus 1. This is an minus 3. Okay, well now what do I have? Now I have 2. I'm going to open a parenthesis. I have 2 times this, I have 2 times this, I have 2 times this, and I have 2 times 1. This is the key. That way I have 1 left over. Hn minus 1 plus hn minus 2 plus hn minus 3 plus 1 plus 1. And now this thing is hn. So an equals 2hn plus 1. An is odd. Can you see this corner?
Where did that one come from inside the parentheses?
If you like it better, I can write this, which you understand, right? Plus 2. Because I have a plus 3, which I want it to be a plus 1, so I move a plus 1 inside because I can multiply it by 2. So because this part is the key, something like proving a number is odd is pretty easy. Because odd just means you have to know what odd means. That's the important thing. You have to know what, if you're showing that some polynomial is divisible by 6, you need to know what that means. You need to know how to say, well, if I know exactly what it is, how do I show that it's divisible by 6? That's the hard part in induction. It seems like a lot of the time the hard part is, people think that the hard part is the inductive hypothesis. It's with 2 S's. What on earth?
It's wrong.
Okay, so now we set up our dominoes. All right, well, we have, okay, A4 equals 3. Ta-da! I guess we need a couple more, don't we? A5 equals 4 plus 2. No, okay, A3 plus 2. No, really? 6 is, yeah, 5 plus 1. Cool. So I did. For a second, I thought it was just going to be all the odd numbers.
Wait, how do you get the A4 to B?
This plus this plus this. No, that's fine. I'm writing everything everywhere.
Over here, so when you put in the parentheses the plus 1, you're saying that if you factoriate this plus 3, where that comes from? Like, trying to think about. Oh, okay. That.
That's all it is. Being able to write down the same equation in 100 different ways is actually an important skill. I don't know how many of you took Calc 2 here. Calc 2, when you do series, don't pay any attention, I guess. You basically, if you can rewrite the same thing in 5 or 6 different ways, eventually it makes sense. But most people have trouble rewriting stuff. They look at this and they say, well, now what? But if you combine your 1s and you get a 3, you say, okay, well, if I multiply this 2 by one of those, I can do this kind of thing. Does everybody get that? Does everybody understand how I used induction? Was that no directed at me?
No, I was talking.
Cool.
I do have a question. Where are we dividing by HN?
Or not. I'm underlining.
Oh, okay.
I'm saying that this guy
Is equal to
is HN. Sorry. You also had a question?
Yeah, I see what you did. We're just trying to follow his template.
Okay. Follow.
Like he goes, okay, assume. Okay, so we kind of just assume they didn't write it. You verbally said the first part works out, and then we're trying to do the second part. But then he says consider k plus 1 to do the plus 1 part. So I guess that's where I'm just.
What do you think?
Because you're just saying that's the definition of being odd.
So what he says is okay. This is the same. Sure. So he's saying consider k plus 1. I wrote that differently. I'm saying consider a n. He says consider a k plus 1. I say consider a n, and then I write down all k's less than n. He says, well, k equal, or for a1, a2, a3, dot, 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 ak. So we're writing the same thing, and I'm writing it using less ink, basically, because I'm lazy. And I also think that you guys understand this version, right? Maybe better than this one, seems like. Or maybe just that they're two different. Okay, assume AK is odd for K less than N, and N is at least 4. He also writes that. Then I just wrote down AN minus 1 equals 2 times this plus 1. And he gives each one of these its own line in his proof. But then he also skips right from here to here. He doesn't write down 3. So I'm glad this is the solution. I'm glad looking at the solution. It doesn't look like high school geometry the way the thing you did. In class, it was all perfectly laid out. Like you could even draw boxes around everything. It was very strictly formatted. But his solution, he's just like, well, I just need a series of true statements that ends with what I'm looking for. So structure, you need to be able to read it. He needs to be able to read it.
Looks like you have like 3 minutes. You want to talk about well ordering?
God.
It's like every
Okay. Do you have your well ordering activity on you?
Yes.
Okay. Because my understanding of well ordering is probably too high. Well, sometimes high level and low level mean the same thing. High level is sometimes, high level means in general. High level also means math 500. Yes. I didn't learn well ordering in 500.
Not yet. It might be.
No,
I don't
it
know,
probably
but we're
is
still-
at 7 o'clock.
Okay.
Oh. Well ordering. Okay. So, yeah.
It's long to do the math.
You have a set of numbers. There is a smallest. That's it. That's it. I don't care if they're non-negative. I don't care if they're integers. I guess I care that the set is non-empty. But any set of numbers has a smallest.
Does that have to be the natural numbers? Any.
If I give you a bunch of real numbers, I guess it has to be natural numbers, yeah. Because otherwise you can make a sequence that approaches 0 from above. Okay, fine. So they're integers. Any set of natural numbers or integers has a smallest.
And when you do proofs with the well-ordering principle, you have to prove by contradiction, right? That the set is not empty, or the set using the well-ordering principle.
Proof of existence. The well-ordering principle, you're going to be given a set of numbers. And the well-ordering principle gives you a place to start. So if you have a set, you have any set of integers, pick the smallest one and start there. And in this example, he says, what's this proof? Proof is every integer greater than 1 is either prime or composite, not both. So yes, you're right. If you want to prove something using well ordering, you assume that the set is non-empty. That gives you a place to start. And then
You find a number that is there.
You assume that it's non-empty. You say, I have a set of numbers that are 2 or bigger and are not divisible by any prime number. Okay, I have a set.
of numbers that fit that description. Let's call this list 1M. Either it's prime or composite, and you'll make an argument that if it's prime, well, then it's divisible by a prime number. If it's composite, well, it's divisible by a prime number. So actually, it turns out that you picked the least element, but it didn't exist. So your set has to be empty.
Well ordering sucks. Hopefully you don't have to do a proof using it.
Yeah, I really like I said, you get this.
Be able to describe it. And if he makes you do a proof on it, I'm sorry.
We're gonna rewrite the, I don't know, / insert creativity here.
12 hours for
Thanks for coming, Aaron.
I'm glad. Thank you for doing this.
No problemo.
Yeah. Oh, that's their playlist. They have a pretty good math part, so their videos. I like